we're going to take a short look at some additional material on find repeats to help you get a sense for some of the material that we may not have been able to cover during our live lecture time. Recall that we had constructed a suffix array. This is a data structure that contains every possible suffix in our fat.rat string. Recall the way we construct it is to initially go through each position of the string and to, at each stage, take the string starting from the point that we're at and taking the rest of it, the suffix, and putting it in the table. So at position 0, the suffix is the entire string. At position 1, the suffix is the entire string starting from the first letter. At position 2, from the second letter, and so on and so forth. Our next operation was then to sort this in alphabetical order, starting from, in this case with our string, at dot. This would be the first string in alphabetical order in our suffix array. Once our entire suffix array is sorted, we then are sure of the property that if we want to find the closest string, starting if we were to do a letter by letter comparison, starting from the first letter, the closest two entries are going to be right next to each other. So for example, if we have an entry AB and an entry ABC, those two entries are likely going to be next to each other unless there's another entry that's even closer, say ABB. With this in hand, we know that if we want to check if there's a repeat of any particular short substring, we can look for that short substring in our suffix array, scrolling down item by item until we find it one by one, and then once we've found the potential substring that we're looking for a repeat of, we just check its neighbor. If its neighbor does not contain the repeated substring at the start, we know that it can't be there because the construction of our suffix array guarantees to us that two adjacent entries are the closest ones there are. If we want to find all repeats of any substring, we do this process for each entry, keeping track to make sure that any entry and its subsequent entry match. If they match, we have found a repeat. Now, one question that we didn't get time to explore in depth was the running time of this new version of find repeats. Well, I'll give you one piece of information for free, and that's that sorting in this instance is mn log n, which means that our total running time for this algorithm is given in 3 steps. The first step, building the basic suffix tree, so running through every position in the string and putting it into our suffix array. Remember, this was our starting from position 0, starting from position 1, starting position 2. So assuming that our string is n in total length, this will give us n steps. Why do we not add extra steps for each individual letter in the substring? This is because in order to store the substring itself, we don't actually need to copy all the letters. What we can do is just say where that substring begins. So substring 0 begins at 0, substring 1 begins at 1. And then when we do the sorting step, the next step, then we'll just rearrange those indices. So for free, I'll give you that sorting again takes, sorting k item takes on average k log k. So if we apply that to our suffix array, we have n items because n is the length of our string. So sorting it is going to take n log n, except for the fact that for each of those, we actually have to do a comparison of up to the first m letters. So we multiply m by that, and to get m n log n for the final running time of that portion. Once we've done that, all we've left to do is traverse our suffix array to find repeats. This we can do in just n steps because there are n entries. Out of all of these, mn plus mn log n plus n, the largest of these is going to be, have a think about it, mn log n, because we know that log n in this case is going to be bigger than 1, and so this will be a multiplicative factor making mn log n bigger than mn, which is bigger than n for all these values positive. And they're integers too. So that gives us the final running time of our algorithm in terms of m's and n's, but let's try this with some reasonable values. So let's say that n is our 1 million. This is our War and Peace with 1 million characters, and we're actually looking for fairly large repeats, let's say of 100 in length. This would give us 4 by 10 to the 9 iterations. Reasonable, which is about 1 second, so pretty fast overall. Let's compare our different methods. So we have our 3 methods. We have our first method, which was the brute force version with no optimization. We have version 1, which had the early termination, so check only up to the point where you're sure that it's not a match. And then we have method 2 with our suffix array. Running this over a number of different possible combinations, if we run it on 10,000 with n as 10,000 characters, method 0 took 1 second, method 1 took just 1/10 of a second, and method 2 took 0.005 of a second running on my laptop. That's pretty fast. But now let's expand it and see what happens at 100,000. At 100,000, these differences become more meaningful. Under a second, obviously, whether it's 1 second or half a second, you're probably not going to notice that. But with a text of 100,000, this suddenly becomes more important, because method 0 takes 1.5 minutes, whereas method 2 still takes under a second. So this is a vast difference in order of magnitude that we can tell. Then, when we get to really large text, let's say 10 million, this is too large for even our early termination method, method number 1, to be of much use. Method number 2 here is much better and takes only 7 seconds for 10 million characters. We can scale this up more and more, and if we get to 1 billion characters, our method 0 would take 3 millennia. It would take method 1 25 years, but it's only going to take method 2 24 minutes. So that's pretty good overall. But we can still do better. If you thought that using a suffix array was the fastest we could go, well, that's not quite true. There are a few ways we could potentially improve on method 2. One way would be use a better string sorting algorithm, so that n log n factor, the biggest one, we could make that a little better, maybe 50% faster with an algorithm called ternary quicksort. We'll see the quicksort algorithm in one of our subsequent weeks, and this is an extension even on that. This takes only 50 seconds to sort about 50 megabytes, which is about 10 million words, and this would take a few hours of programmer work in order to do. We could also improve the way that we build our suffix array. So even though the runtime is going to be dominated by our mn log n factor, we do probably want to improve the mn factor as well if we care about more than just the asymptotic complexity. So maybe we could speed up our construction, maybe doubling it in speed, and this would take potentially a few days of work, and give us some slightly better algorithmic complexity in the full sense. But even after all of this, we can still do better. Well, if we go and compile our code and look at the assembly language that it produces, we might see that some of it could be made a little faster for the particular design of the chip architecture on which we're running our code. So with a lot of manual labor and expertise, we could write our own assembly code that is more optimized for the way that our particular machine processes instructions, perhaps cutting our runtime in half again. This is probably optimistic, but let's say we get there. We could still do even better. Not only could we run our algorithm on a single chip at a time, but we could run it on a multi-core chip in parallel. This here is a cross-section of an Intel chip. Let me count them. 1, 2, 3, 4. I think there are 10 cores on this chip. So this is a hefty, expensive chip that you'd find only in a server or a very high-end desktop. Maybe we can take advantage of this. But our algorithm doesn't parallelize, which is a bit of a shame, because in order to take advantage of all these extra cores, we need some way of splitting up the work into different chunks and then combining it at the end. We do have actually a pre-coded solution for this, and this is our method 4. It does use significantly more storage, which means there's a space-time trade-off, and it's also a bit more complex, which means it doesn't run as fast when you just have a single core, but it can process 100 million strings in just 7 days, or 10 minutes if you spread it across 10,024 processes. So the 7 days doesn't sound so good, but as soon as we run this on a large computing cluster, this suddenly becomes very, very powerful, showing us that parallelism can be one way of obtaining even better practical speedups for our algorithm. In one instance, it's really important to ask, what's the asymptotic complexity of this algorithm? And on the other hand, it's also important to ask, well, practically, for my use case, what are the values going to be? And so how should I design my algorithm to make it the best trade-off in terms of the amount of work I put in, the amount of resources it uses, and the amount of time it takes to get the work done for the given scenario? Ask yourself, what will your algorithm actually be used for? And this is the key to good algorithmic design. And also, what makes computer science fun? The ability to go in and solve a problem on all of these different levels and think about all the different cases in which it might be used, then applying it to your case, is the heart of why I enjoy this and why I hope at the end of the semester you will too.
I'm designing a machine that will allow us to break every message, every day, instantly. I'm just a mathematician.
Sometimes it is the people who no one imagines anything of, who do the things that no one can imagine.
And remember, after all of this, algorithms are fun. I'll catch you later.